Hey guys, in our last lesson we talked about forces and we talked about how to draw force diagrams or free body diagrams, right? We're going to go on here, we're going to talk about the laws of motion. There's 3 laws of motion, and in today's video we're going to talk about the first law of motion. So our target here, we want to be able to describe the relationship between the force acting on an object and that object's motion. So let's go ahead and let's talk about the first law of motion. Okay, the laws of motion were come up with by Mr. Sir Isaac Newton. You may have heard of him. Kind of a big name in physics. In the 1680 something maybe, Isaac Newton published a book called the Principia. It's kind of the foundations of physics, the entire subject of physics. It's an interesting read if you like reading Shakespeare and you like reading about math. I highly suggest the Principia because it's math written in Shakespearean language. How could you go wrong, right? So in the Principia, Isaac Newton lays out his laws of motion, the law of gravitation, lots of different. Oh, he invented calculus. So I mean, kind of an important book. And he uses his new laws to kind of make predictions about some of the different physical phenomena in the world. So that's kind of interesting, and you can see, his predictions based on his laws actually work. So cool stuff. 3 laws of motion, like I mentioned. Today we're talking about the first one, and Newton's first law of motion. It's called the law of inertia. It states that an object at rest will remain at rest, and an object that's in motion will remain in uniform motion unless a force acts on it. Okay, so an object at rest will remain at rest. An object in motion will remain in uniform motion unless force acts on it. It's called the law of inertia. Inertia is the tendency of an object to kind of resist a change in its motion, right? If you think about, like a pebble and a boulder, which one's going to resist a change in its motion more? The boulder, right? Something with more mass will have more inertia. And so the first law is called the law of inertia. Cool stuff. Okay, so here I have a super complex demonstration of the first law of motion. There's a marker. That's an object, and it's at rest. It's still at rest. Ain't nobody applying a force to this marker. It's still at rest. And guess what? It's going to stay at rest until you put a force on it. Look, it moved. I applied a force, it moved, right? Okay, so there's an object. It was at rest. It stayed at rest until I put a force on it. And that's the first law of motion. The other part of the first law is a little bit more difficult to demonstrate, and that's an object in motion remaining in uniform motion, remaining in motion with a constant velocity, unless a force acts on it. If I were to, let's say, shove a book across the floor or something like that, sure, you have an object in motion, but it's not going to remain in uniform motion because there's a force working on it. If it's sliding across the floor, that force is the force of friction, right? If I were to throw a ball through the air, then it's not going to remain in uniform motion because there's a force working on it. It's gravity and that's air resistance, so it's not going to remain in uniform motion with a constant velocity. So it's a little bit harder to demonstrate. If you can envision it, though, I mean, think about out somewhere in outer space with nothing around you, and there's an asteroid moving along. It's going to move along at the same velocity. Its velocity won't change unless some force comes along and works on it. So that's the other part of the first law. So, the object at rest remains at rest. The object in motion remains in motion unless a force works on it. Basically, the first law says the velocity don't change unless you put a force on it. Okay, so what if we do have a force working on our object, right? Sometimes we're going to have an object and it's going to have two forces working on it. It's going to have three forces. It's going to have four forces, right? And what we're going to need to do is we're going to need to be able to find the sum of all of those forces. All of those different forces, the sum of those forces is what's called the net force. And oftentimes when we talk about the net force, we'll use a little sigma, the Greek letter sigma. If you remember from math, sigma indicates summation notation. And if you put a little sigma in front of F, that means that's the net force. It's the sum of all the forces. So let's talk a little bit. Remember, force is a vector. So when we need to add up all the forces, we're doing vector addition. So let's go ahead and let's take a look at some of that and talk about how to find the net force acting on an object. Okay, let's take a look at how to add up some vectors, some force vectors here. Here's an example. It says, Derek leaves his physics book on top of a drafting table that's inclined 35 degrees. The force diagram shows the forces acting on the book. So we have here the force of gravity acting on the book. It's 22 newtons, and that's in a straight downward kind of direction. That's entirely vertical. We have the force of the table pushing up on the book here. That's 18 newtons in kind of this direction. And then we have the force of friction working on the book in this direction of 11 newtons. Okay. So what we're going to do is we're going to take each of these three vectors, resolve them into their vertical and horizontal components, and then add them up. So I'm going to make myself a little chart here. Okay. Here I'm going to put the vector's horizontal component. Here I'm going to put its vertical component, right? And there will be these three vectors. And let's start with the force of gravity here. That's a nice easy one because it's entirely vertical, right? So in the horizontal direction, here, let me put the force of gravity here. There is nothing in the horizontal direction, right? So it's entirely in the vertical direction. But let's keep in mind this vector is pointing in the downward direction. So I'm going to call that negative. So it's negative 22 newtons in the downward direction. So that was a nice easy one. Okay, let's do one of the other ones next. Let's see, let's take a look here. How about the force of friction next? That should be pretty simple. The force of friction is acting at a 35-degree angle, right? So it's acting this way, and that's a 35-degree angle to the horizontal. So that should be pretty easy to figure out the components. Force of friction there. So to figure out the horizontal component, remember we just take the amount times the cosine of the angle. So to figure out this, we'll take 11 times the cosine of 35. Get my handy calculator. 11 times the cosine of 35. And I get 9.0. We need two significant figures. 9.0. Now let's keep in mind that that's acting in the negative direction. So I'll make a negative. To figure out the vertical component, we'll do 11 times the sine of 35. So 11 times the sine of 35. Two significant figures, we'll call that 6.3. And since that's upward, upward is in the positive direction, right? So positive. Okay, and then we have this third force here, the book pushing, or the table pushing up on the book. We'll call it Ft there. This one is a little bit trickier because this vector is not 35 degrees. See, this vector was at 35 degrees, but this one is perpendicular to that, right? So here, this is 90 degrees here. So 35 degrees, and this is 90 degrees. So we need to figure out, here's a horizontal. We need to figure out how much is that angle, because that's the angle that we need, right? So, okay, so if this was 90 degrees and there's 35 degrees and it's 180 degrees all the way around, I'll take 180, subtract that 90, subtract that 35. We've all taken geometry, right? Subtract that 90, subtract that 35, and it's 55 degrees. So that angle is 55 degrees. So now to figure out the components, we'll just take 18 times the cosine of 55, and then 18 times the sine of 55. And these should both be in the positive direction. See, it's to the right and it's up, so they should both be in the positive direction. So 18 times the cosine of 55, that's about 10, two significant figures there. And that times the sine, that's about 15. Okay, so we've got our three vectors resolved. Now what we'll do is we'll add the components. So the total force, the net force, what we might call sigma F, right? I'll just go through and I'll add these, and let's see, 10, negative 9, gives me 1, we'll call it 1.0. And then we'll add these up. I got negative 22, got 6.3, I got 15, and then we get negative 0.7, we'll call it 0.70. Okay, so these are the components of the answer. These are the components of the net force, right? So what we'll do is we'll recombine them using the Pythagorean theorem, right? So c squared equals a squared plus b squared. We'll put those in there. These are a and b. So 1.0 squared plus negative 0.70 squared. And let's see how that comes out to you. Let's see, 1 squared is just 1, 7 squared, and that is 1, it's about 1.5. We'll get the square root. Get about 1.2. And being a force, that'll be in newtons. And then we should probably figure out what direction is the net force, right? So we'll use the tangent inverse here on this. So if this is, let's see, this is the horizontal, so it's kind of 1 this way, and 0.7 this way, and it's working in that direction. So let's figure out this angle right here. So we'll do the tangent inverse, if theta equals the tangent inverse of the opposite side over the adjacent side. So the tangent inverse of 0.7 over 1. And there we get, so let's see, theta equals, that is, that's 35 degrees. Isn't that interesting? This one was 35 degrees, and then this one is 35 degrees. So the net force is going straight that way. Pretty cool. Wasn't that a fun example? So basically adding vectors to find the net force. Fun stuff. So hopefully that helps us get a step closer to being able to explain the relationship between the force acting on an object and its motion. Until next time, take it easy.